Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Right, question 27 states, suppose that the plutonium-239 nucleus fissions into two fragments whose mass ratio is 0.32 and 0.68. With the aid of figure 32.8, estimate the energy in MeV released during this fission. So I drew out kind of here what graph or what figure 32.8 is showing. So it shows for a given nucleon number on our x-axis here, the binding energy per nucleon on the y-axis. So the scenario we're presented is that we have this atom of plutonium-239, and it splits with a ratio of 32% and 62%, where it's something where we have nucleon A's, I'll say not A, I'll say nucleon X. The first one has 76 nucleons, or actually atom, and atom 2 has 164 for Y. So this is, in terms of nucleon number, this is 32%. In this term, it would be 68% of the original provided to us. So maybe a little bit hard for me to do exactly what I did to solve this problem in this graph, in this example, because I need to look at the graph. So I solved this by first looking at what the graph tells us, and then for each of these values, for 76, I looked on my x-axis here for value 76 and found the corresponding nucleon energy, so binding energy per nucleon. And for 76, this one I found approximately is 8.85 per nucleon. Did the same thing for 164, which is maybe somewhere around here. My graph is definitely not to scale, but this is the idea. So here this was X, this one was Y. I found that this Y term has approximately 8.05 MeV per nucleon. And the same for plutonium Pu, which is approximately 7.6. So again, this is, you cannot gain this information from the graph that I drew, but you do need to look at the figure in the textbook 32-8 on page 991. Yes, 991. And so if I were to find the total binding energy, well, of course, we could say it's the final energy minus the initial, or as it's phrased in the question, we're looking for how much energy is released during this fission. I'm going to put approximate equal to because these values that I have are approximate, of course, based on what I can read from the graph. So for our final terms, for the first term, we have 8.85 MeV per nucleon for 76 nucleons, and 8.05 times 164. Again, these are the mass ratios based on what's given, and we subtract off our original term of 7.6 MeV times 239. Oh, and I just realized a small mistake. Let's see, this is 76 plus 164 does not add up to 239, so this is 163. Apologies for that. And same here, 163, although it doesn't affect my calculation or my process, but these values that I have, again, this was based on 163, not 164. And we find that this difference in energy, what I could tell from the graph, was 168 MeV, and approximately equal to, again, because it is pretty difficult to read exactly what the values are, especially on a textbook, a digital textbook. Probably be a little bit easier if I had the textbook in front of me. But this is what I have. And in the textbook, it does say that this value is 160 MeV. But again, that may benefit from me more having the textbook in front of you and calculating that way. But regardless, if you do say based on looking at the graph, These are my binding energies per nucleon. That should be a sufficient method to calculate this question. So there you go.